everyone. Thank you for coming to my talk today. And I want to thank Paul Ayers and Tucker Carrington in particular for organizing this session. So my name is Paul Johnson. I work in strong correlation, specifically using wave functions from exactly solvable models. Generally, the work that we do is very mathematical in nature. I understand that not everyone enjoys looking at thousands of equations in a row. So my presentation today will mostly focus on the bigger picture and the shape of the results along with some numerical examples. Okay, so as a motivating long-term goal, and you can joke, I have the idea that long-term is perhaps in my lifetime. We can joke about whether or not that's long-term or not. We want to look at big systems that are not easy to solve. So molecular magnets that are couplings of two very different behaviors, where there are spins of one type in blue and spins of a second type in green that couple together to form a non-trivial thing. There's a lot of effects going on here, and you would hopefully see that this is not just a Hartree-Fock plus small correction example. There's many Slater determinants that we would need to include, and it's not easy. It's a lot. Now, manganese acetate is a prototypical example. There are much more difficult cases that we would also like to be able to treat that are larger and are heavier and hence have effects of special relativity, etc. So to be able to predict the behavior of these complicated systems, we have a very difficult, strongly correlated electronic structure problem to solve. There are non-trivial effects due to special relativity, and we need to do all this at a finite temperature. So let's do this how we solve any problem. Let's break it down into easier, one problem at a time type things. So let's focus on strongly correlated electronic structure problem. On its own is not trivial. So I understand that there's perhaps disagreement on what we mean by strong correlation. So let's just review the way I think about it. Weak correlation effects is anything that is well described by one Slater determinant, one molecular orbital diagram. Hartree-Fock is the correct qualitative picture. So for molecules with one resonance structure, one Slater determinant, a large homoluminal gap compared with the electronic repulsion of the valence electrons. Strong correlation, on the other hand, any process involving bond stretching or breaking. Why? Because more than one Slater determinant will, of course, be required to describe that correctly. Any situation where motion of electrons is rigidly coupled, where there are many resonance structures to describe the ground state, and so many Slater determinants, when the homoluminal gap is small, or in any situation where you find it productive to ask the question, how many bonds are there? Generally, that's a sign that Slater determinants are not the correct picture. There is strong electron correlation. So any system where there is not a mean field of electrons that describes the system qualitatively. Okay, so what's an approach that we could take to solve this type of problem? How do we solve any problem in physics? We start with an easy problem that we can solve exactly, and then we add on systematic corrections that are hopefully small in comparison. So for weakly correlated systems, this is very well studied and the approaches are very good. We start with Hartree-Fock, which is a very good first approximation to the precision that we want. And we add on systematic corrections based on excited Hartree-Fock states. Now this converges in sarcastic air quotes, provided Hartree-Fock is a good first approximation. If it is not, then this is not a productive area of discussion. So the approach that we like to take, and we are not alone, is we would like to think of a reference that is not a single Slater determinant, that has a better description of the mean field behavior. And we would like to build our complicated wave function in the basis of those states. So strong correlation is many, many different effects. It is in general any effect that is not weakly correlated electrons. So let's try and subdivide that further so that we can, make some measurable progress on this. And the easiest or most straightforward, perhaps, first step is to think about weakly correlated pairs instead of weakly correlated electrons. So this is not itself a new idea. A lot of groups have been thinking about this for a long time. AGP in particular has been around since at least the 60s. mainly due to Coleman in the beginning and others, and I will not be able to name everyone involved, so I apologize. The groups with which I'm very familiar, or at least recently, are those of Gustavo Scuseria, who's also presenting in this session, Paul Ayers, who is also working in this area, and our group who is doing something in this area. So all of us are thinking in terms of pairs of electrons rather than individual electrons, and this leads to wave functions that we can deal with and are better for some strongly correlated systems. Not all strongly correlated systems, for the reasons we mentioned just a second ago. In particular, they are better for systems that have seniority 0. So seniority, we can say, is the number of unpaired electrons in any given Slater determinant or MO diagram. DOCI, or doubly occupied configuration interaction, would be the exact wave function if all the Slater determinants had seniority 0. So any pair mean field or Geminal wave function that we use is going to be an approximation to DOCI, hence we will compare it to DOCI. Again, this is not all strongly correlated systems, but it is a first step, and it is already a fair enough fraction of strongly correlated systems. So we're going to work on this in this area for the time being. Okay, so the algebraic picture that we work in. For individual electrons, it's very easy in second quantization. We have two objects. We have creators and we have annihilators, and they have a structure of anti-commutators being equal to delta ij. That's it. We build all our states out of A daggers and all of our dual states out of A's, and we can take scalar products very easily with something called Fick's theorem. Pairs can be made with these objects. Instead of 2 objects, we end up with 3 objects, an S plus, which creates a pair, an S minus, which removes a pair, and an SZ that counts the number of pairs in a site. These 3 objects have very easy commutation relations that you will recognize from undergraduate quantum chemistry. This extends very easily to any number of sites. So we create pairs in site I, we remove pairs from site I, and we count the number of pairs in site I. The only difference for the commutation relations is they are decorated with Kronecker deltas. So instead of building orbitals out of A daggers, we build Geminals out of S pluses, and there we can make states out of products of these things. So there are many different Geminal products, and we will discuss them very quickly. The simplest possible Geminal being restricted Hartree-Fock, where each Geminal is just one pair object. Next, we have anti-symmetrized Geminal power, where all the Geminals are the same. If pairs of electrons were genuine bosons, this would be much closer to the exact answer. It is not. The type of Geminals that we will be using are called Richardson-Gaudin. They are parameterized by 2 sets of numbers, and we will see that in the coming slides. The best possible Geminal of this type is called APIG, where each of the Geminals is parameterized by a set of Geminal coefficients. This wave function itself is intractable, but AGP and RG states are tractable. Okay, so there's another type of Geminal product wave functions that are are known in literature. They fall into the class of making a separation of your orbitals into occupied and virtuals. And it's perhaps most easily seen if we look at AP1ROG, or what is equivalent pair couple cluster doubles. There, each Geminal has one occupied virtual, and then one occupied orbital, and then coefficients coming from each virtual. If we expand this in a couple cluster fashion, this is very easy and cheap because it's Slater determinant. It's one Slater determinant plus pair doubles. That is it. APSG is a special case of this, where each of the virtual coefficients are disjoint. So each Geminal has a set of virtuals, and they only contribute in one Geminal. Further, GVB, or perfect pairing, is a further special case where each Geminal is one occupied and one virtual. So these are also known in the literature. They are very good in 2 cases, either when the wave function, the physical wave function is Hartree-Fock plus doubles, in which case pair couple cluster doubles is pretty much exact, or when the wave function is GVB, in which case it is also pretty much exact. We are looking at Richardson-Gaudin states as our Geminal, so let's describe those briefly. They are eigenvectors of a physical system. It is a physical system you've probably not seen before unless you've heard me talk. So they are eigenvectors of this particular Hamiltonian, which is a competition between two effects of alpha filling the lowest levels and pair scattering between each site. You can easily show on a few lines that if you act with this Hamiltonian on a product of RG pairs, you will get one term that's proportional and a whole bunch of linearly independent garbage. Now it's an eigenvector provided that the garbage disappears numerically. And how do you do that? You solve a set of nonlinear equations for these coefficients. Okay, so this Hamiltonian is defined by single particle energies epsilon and a pairing strength G. You solve the nonlinear equations for the U's, and you have to solve a set of equations that are coupled for a single set of U's. There are many different solutions for each set of epsilons and G, but you can solve for them all very easily. Effective numerical algorithms exist. This is a solved problem. It is easy to find all the eigenvectors of a single Hamiltonian. Once you have one eigenvector, what you would need to evaluate the energy of a physical Hamiltonian is its expectation value. So the scalar products are easy. There is a known theorem that says that it is a determinant of a specific matrix scaled by a function of the sets U and V. You can find the norm of this state very easily by taking the limit as the sets are the same. It is a determinant of a matrix that has a physical interpretation. The 1RDM elements are very easy to compute. Without going through any of the details, what it reduces to is a sum of things that you can solve linear equations for. Similar expressions exist for the 2RDM elements in the same sets of linear equations. So to evaluate the energy, the expectation value of the physical Hamiltonian that we wish to solve with these wave functions, all you need to do is linear algebra operations and then take linear combinations of those things. Very, very clean, easy. Now, most of the work that we do in our group is making the computations to be done easy, and that is a lot of hard work on paper, and we will not talk about that at all. But the message is we do hard work on paper to yield easy expressions for computers. All that the computers have to do in the end is linear algebra operations and optimization with off-the-shelf routines. Okay, so with all that in mind, we look at some results. The first case that is prototypical is a dissociation of a hydrogen chain, which is like a Hubbard model. H4 dissociating into 4 separate hydrogen atoms is a strongly correlated system where the bonds, again, not a productive question. Near the minimum, we get the correct answer, or we get very close. We get qualitatively the correct answer. Why? Because it's Hartree-Fock. At dissociation, we get the correct answer because it's pairs. In the middle, we have an avoided crossing because the transition between the two is not so easy. This gets worse for H6 for the same reasons. At the minimum, it's Hartree-Fock. At dissociations, it's pairs. In the middle, it's an avoided crossing of the two. It is worse for H8 for the same reason. And the message here is that we are going to need more than one RG state to describe these systems correctly. But the expansion will be short. So we also looked at nitrogen. At the minimum, it's close to DOCI. At dissociation, it's exactly DOCI. In the middle, it's not so bad, but DOCI itself is not great. So the point is that we can get DOCI in a basis of RG states if we work, and it's not even a big expansion. Okay, so I'm very quickly running out of time, but the point I want to make in these last couple of slides is that RG states are not a difficult basis in which to work. You can evaluate everything you need to evaluate very easily. All the hard work on paper has already been done. So the states are very easy to identify, and you can solve the equations very easily for each state. There are only 2 types of matrix elements plus an RDM you need to compute. And while they don't go to 0, while they're not identically 0, they go to 0 quickly. So you can see this very clearly. If you look at bigger systems, these singles are important, the doubles are important. Past that, it is 0. Now, Hartree-Fock is good because you can write the wave function in the basis of molecular orbitals, and past doubles, it is identically 0. That's not the case here, and we'll just brush past that. Okay, so the message, weakly correlated, you write an expansion as Hartree-Fock plus small corrections, and that is an appropriate approximation of the wave function. Seniority 0 is strongly correlated. Our point is that we can do exactly the same thing, and we can improve systematically. And The cost is not bad. We can do singles, doubles, etc., and we can improve this systematically. The outlook is that we are building states we are building wave functions for strongly correlated systems with exactly solvable models. In particular, for the moment, we are using Richardson-Gaudin pairs. The advantages are this is variationally very feasible, computing the energy of a physical Hamiltonian costs into the fourth. We have not said anything about the optimization because that is as yet an unsolved problem. We get a complete set of eigenvectors that are linearly independent. They're eigenvectors of a Hermitian model, so they're orthogonal. And all the expressions are easy and clean. We have some near-term challenges. How do we get initial guesses? We need to work on the optimization. The transition density matrices are a bit expensive, and we need to optimize the orbitals. These are all manageable problems that will be solved. And the takeaway message is that the machinery to use these states as a basis for quantum chemistry is not difficult. It is solved. The hard work has been done. If you would like to use these states, please get in touch and I'd be happy to work together. So with that, I'm out of time. So I'll thank all the group members who worked hard on this project. And if you are interested, please contact me. Thank you.